Hey guys, welcome back to a new Insane Builds video. This is going to be about this Tesla coil I'm currently building. Before that, I hope you guys enjoy. Anyway, this here is, I guess, a mini thing I've done. It's a mini ZVS drive. See here, got some mini plasma arcs. Turn this off. It's getting very hot. Anyway, I'm going to talk about the I guess Tesla coil so far. Hi guys, I've cleared up this workbench a little bit. I guess I want to talk to you about what I've done so far. So this is obviously the power supply. If I get the circuit diagram out for the actual Tesla coil, you can see here, this is what I'm trying to do. So I've currently made the power source. This here has the resistance as well. You can see the resistance is right here. Now, this resistor was initially meant to be 1250 ohms, but because one of the resistors didn't work, I have to use two. And because they're 500 ohms each, I've got approximately 1 kilo ohm. So if I go and measure it with my LCR meter, you guys can see here that I'm getting approximately 1 kilo ohm, which is correct because they're two 500 ohm resistors in parallel. Okay, you guys can see here, this is the capacitor bank. So what this is this section, it should be this part right here. This is going to be what oscillates the tank circuit. As you guys can see here, this is then connected to the primary of the Tesla coil, which is this part here. So this is the primary part, and this is the secondary coil. So it's going to be something like this here. Hey guys, as you can see here, I just rigged up my Tesla coil winder. It was literally took me like 2 minutes to do. I just used like sticky tape so it can rotate freely on that. And then I put my the 30 AWG copper wire on an Allen key, which is just, it basically just acts as a spindle. So when I spin this, it in turn spins this as well. Anyway, I winded the whole thing up. It took me about 5 hours ish. I was too lazy to attach like a screw system that spins something around here. So yeah, I mean, it could have been worse for sure, but it did the job. So that's really all that matters. Yeah, as you guys can see, when I spin the coil, it spins the wire, and yeah, I mean it spins freely. So this is just a book I put in there to act as a counterbalance, so it doesn't like go like that. Yeah, that's about it for my Tesla coil winder. You guys can see here there's a primary coil. I am missing one thing actually, which is the feedback coil. You can see the feedback coil is going to be here. This is basically how, well, this is a Class C Armstrong oscillator. And if you don't know how a Class C Armstrong oscillator works, I talked about it in one of my previous videos. This is just using a high-powered vacuum triode as an alternative to a MOSFET or whatever, which I did in the previous video. Okay guys, with the power supply. So what this is here is, if I draw this on the left, here, pen, this here is a transformer. And this transformer is then going to be put through some bridge rectifier. So it's going to look something like this, I believe. Okay, and now this section here is actually going to be put into an LC. It is called an LCR. This section here, LCR filter. You guys can see here, this is purely made for microwave parts, by the way. So you have the capacitor bank, one here. This here is an inductor, and this here is the other capacitor bank. So it's going to look something like this. If I just draw this output like that, let's connect to one part here. look something like this. So this part is going to be the DC input, so this section here is going to go here, and then the output of the LCR filter is going to be this terminal and this terminal here. You can see it's coming off this capacitor. You can see here that it comes off the end of the capacitor here. As you can see here, each capacitor is approximately 2 microfarads, so I'm just going to rub this out. Each capacitor is approximately 2 microfarads. So we have 5 capacitors on one side, and then we have 5 capacitors on one side, which would equate to around 10 microfarads, and then we have 4 on the other side, which is 8 microfarads. So if we want to calculate the energy of those capacitors, right, in joules, we can do something. So we have 2 capacitors in parallel, so there's going to be approximately 18 microfarads. We can then say that the energy is going to be equal to this, the capacitance being, and then it's multiplied by the voltage, which is going to be 3 times 10 to the 3 all squared, because the output voltage I'm trying to get from this transformer is around 3000 volts. I'm going to explain why I'm trying to get 3000 volts. Before that, if you calculate this, I'll put the value on the screen, I'm not sure what it is right now. But yeah, you'd get a lot of joules, and if you don't know, for reference, 1 capacitor is approximately like 2 joules of energy, and anything above half a joule can kill you instantly. So this being such a high amount of joules, if you touch the 2 terminals when it's live, like, you would easily die in a couple seconds. Not even a couple seconds, you die instantly. Like your whole hand will probably explode. Anyway, I'm just showing the dangers of this system here. So besides that, the rectification, you guys probably can't see, it's actually underneath the whole transformer. So if I disconnect some terminals, I should be able to flip this around and you guys can see the rectification stage. Okay guys, so I flip this thing around. As you guys can see here, this is 4 microwave diodes. Then there's just 4 in general, there's not like a multiple in series or parallel, whatever. This is because it can handle the voltage rating of a single microwave transformer. Yeah, anyway, it's converting around 2000. If I just show you the calculations here, the output of the microwave is this, and now we're rectifying it, right? So it's going to be 2100 times by square root of 2 over 2, which, Jesus, it would be around, I think, 3000 volts DC, and then because we have 3000 volts DC coming out from here, the reason why I'm feeding it through this sediment filter here is because it's going to be something called voltage ripples. When you have your rectified voltage, this is at 3 kilovolts by the way, you're going to have mini voltage ripples across it, right? This is just a diode and stuff like that. Anyway, it doesn't matter. You can see here that for me to minimize the voltage ripples, to decrease it, I need to use capacitors, right? Because in a sense, a capacitor stores energy in the form of electric field. If I store the electricity in the form of electric field, I can basically store more energy. And so when the load changes across the power source, the capacitors can instantly charge it. And then the inductor, I'm not going to really get into that, it's kind of pointless. It has a useful point, but I can't really be bothered explaining it. So yeah, anyway, now when I'm looking at the circuit here, as you guys can see here, I have a, well, this is a 1000 ohm resistor, because obviously I told you the other resistor broke. Anyway, so the whole point of this specific resistor here is to bias this whole tube here. As you guys can see here, you have something GKA. What this is here is this is the amplification stage. So basically it's gonna look something like this. Is this section here. Yeah, anyway, if you don't know what this is a vacuum tube. You can see here, I had my hands on a vacuum tube. It actually broke. I'm gonna have to get a new one. I don't know if you can see in here, but the tungsten electrode, which is connected to the filament, which is this section here. Basically the filament causes thermonic emissions, which allows for conduction to occur across both the cathode and anode. Anyway, yeah, it broke. I don't know how, but it broke. So I'm gonna have to get a new vacuum tube. This is a 500Z vacuum power trod. You guys can see here. Yeah, anyway, yeah, it's a bit annoying how it broke, but I can't really do anything about that. If you don't know, this is operating at a frequency of 100 kilohertz. I've tuned it and everything in the circuit. I'll show you guys after. I also had to run a software to actually design a vacuum tube, which took like so long. Oh, hey guys, in this software, this is the L2 Spice simulation here, as you guys can see. Well, I've currently built the whole circuit in here. So you guys can see here, this is the power supply. It's operated at 3000 volts DC, and it's been pulsed at, I believe, around 100 kilohertz. I won't really explain that right now, but you can also see down here, this is the coupling efficiency. It's rated at 1, so this is just to remove any losses between induced voltage. As you guys can see down here as well, this is now the vacuum tube. Because I'm using the vacuum tube to act in the amplifier stage. If you guys don't know, LT Spice doesn't actually have vacuum tubes in their software, so I had to go for this massive, rigorous software I had to program a vacuum tube basically. I watched a YouTube video of this guy doing it. It was pretty straightforward, but there was a lot of it took me about 2 whole days, a very long time to get this working. Even so, I am using a 3-500Z vacuum trod. The downside with this is the actual data sheet is running positive grid voltage, and I'm running a negative grid voltage here. I was kind of winging it, but yeah. Anyway, you guys can also see down here this is basically just, I guess, setting the command when the forward voltage equals 0, it conducts, and when it's equal to 100 mega ohms, this voltage current can't travel across it because the voltage drop across the vacuum would be too bad. Anyway, yeah, these are the formulas that was part of the Quran formula. Anyway, this up here now is the actual Tesla coil circuitry. It's oscillating at around 1.1 megahertz. You guys can see this is the top load capacitance, which I measured in the software, and then the secondary coil is 30 millihenries, as you can see here. All Tesla coils have a top load with the capacitance. And then this here is the oscillating circuit down on the other side. It's going to oscillate with the secondary coil. Well, the primary coil is going to act as a primary, I guess, transformer. So yeah, so this whole oscillating section here will induce a voltage into the secondary coil. Anyway, now when I simulate the actual software, you guys can see here that well, just right when I load it up, yeah, when I measure this, when I simulate it and I see the voltage across the Tesla coil, you can see here that it's around a megavolt, right? So the distance across here is around it isn't actually 1 megahertz because I'm pulsing the frequency at around I believe it's 300,000 kilohertz, no, 100 kilohertz. So yeah, this isn't technically a megahertz, so I'll have to change the pulsing frequency. The main reason why I actually have a pulsing frequency is because I wanted to incorporate a spark gap vacuum tube, which has never been done before. I've never actually seen people have spark gap vacuum tube Tesla coils before. I'm not sure why. But I want to be like, this is one of the first iterations of it, and I think it'll be pretty cool to show that.